Hi Bobcats! This video is going to introduce molecular orbital theory. We're going to look at the ideas behind molecular orbital theory, and we're also going to generate some MO or molecular orbital diagrams, energy level diagrams, for the first row homonuclear diatomic molecules, and also introduce some of the vocabulary that is peculiar to molecular orbital theory, including what's the difference between bonding, anti-bonding, and non-bonding MOs, what's a HOMO and what's a LUMO, and what is bond order. Valence bond theory does a pretty good job of explaining some fairly simple molecules pretty well, but molecular orbital theory allows us to use some of the same ideas but expand them to much bigger molecules. In sort of the short version of molecular orbital theory, we're still going to start with the atomic orbitals like s, p, d, but we're not going to use the orbitals from just one atom or even the orbitals from just two atoms. We can combine those atomic orbitals from as many atoms as we have in the molecule. And so we'll mathematically combine them, like that process of taking linear combinations, and the resulting molecular orbitals will span the entire molecule in some cases. Some cases they won't go all over the molecule, they may be just over half the molecule, or maybe even just on a single atom. But we're going to get a huge variety of these molecular orbitals. And one of the indications that we need to invoke molecular orbital theory to describe the bonding in a species is that when we draw its Lewis dot structure, we need resonance structures to have a good description of the molecule. In just a moment, I'd like for you to go visit this website. This website, the thing I like about it is that just in one screen, it's going to show you a molecular orbital energy level diagram. That's going to be on the right side of the screen. And in little itty bitty pictures over there on the energy level diagram, it's going to show you sketches of the different MOs that are created for benzene. And then if you want to see a bigger version of that sketch, click on it. Click on that little itty bitty sketch and wait just a moment, and a model of that MO will load on the model of benzene that's over there on the left side of the screen. I just realized that says right there, and that should say left. And what's over there on the left side of the screen. If you look at these different molecular orbitals, there are some that are up there high on the energy level scale that are just on a single atom, so they're basically just like having atomic orbitals, some that span two, but some of these molecular orbitals span 3 or even all 6 atoms in that central carbon ring. We consider those electrons that are spanning multiple atoms to be delocalized. These molecular orbitals are spanning as much as the entire molecule, and the electrons, a pair of electrons that can be in any one orbital, could be anywhere throughout that entire molecule. And so when that happens, we call those electrons delocalized. So hopefully you took a moment and you went and looked at those benzene molecular orbitals. What I'd like to do now is tackle the simplest molecules that we could possibly make. Over here on the left-hand side, I want to tackle hydrogen, H2, and over here on the right-hand side, I want to tackle He2. Okay, so let's kind of unpack the words here a little bit. We're talking about first row. That means the first row of the periodic table. So that's hydrogen and helium. And then homonuclear. Homo means the same, so we have the same nucleus, so that means two of the same atoms, because we're saying diatomic, so two atoms making up these molecules. So we're going to do hydrogen and we're going to do helium. Now you're telling me, hold on a minute, you've already told me that helium's a noble gas, it's not going to bond anything. And you know what? You are right. One of the things we're going to show is that based on this theory, He2 isn't going to form. So that's also kind of validation for this theory, right? We know He2 doesn't form, and this theory predicts, no, it will not form. Okay, so when we go to build the energy level diagrams for hydrogen and He2, each hydrogen atom brings a 1s orbital into play, and that's shown on the far left and the far right. And since hydrogen has one electron, I'm going to draw one arrow to show one electron in each one of these orbitals. So if we have separated, isolated hydrogen atoms, that's what its electron configuration looks like, 1s1. But when we bring those two hydrogen atoms together and allow for orbital overlap and all that wonderful sort of stuff, molecular orbitals can form that we're going to call sigma 1s and sigma star 1s. The sigma 1s is lower in energy than the two separated 1s orbitals, but the sigma star is higher in energy. And if you take the average energy of the sigma orbitals and the average energy of the 1s orbitals, you'll end up with the same thing. So we aren't really in the big picture doing anything funky with energy levels, because it all works out to be the same. But we can say that hydrogen likes to form a bond, because when we put these two atoms together and we start using the sigma orbitals, we have two electrons to go down there into that sigma 1s orbital, and their energy overall is lower when they are in this molecular orbital. When we go to a lower energy situation, then the bond will form. If we look at He2, each helium atom has two electrons, so we'll start off with two electrons in the 1s orbital in these two separated helium atoms. But then if we bring those two helium atoms close enough that they can interact and form molecular orbitals, we now have 4 electrons to put into our sigma orbitals. So we'll start by putting electrons into the lowest energy orbital. By the Pauli principle, we can only put 2 in here. Then we have to go up to the sigma star. All right, so now let me introduce something called the bond order. In order to calculate the bond order, which I'm going to abbreviate BO, we're going to calculate this by this very simple formula of 1/2 the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So the lower energy molecular orbitals are referred to as bonding, and then the higher energy molecular orbitals are referred to as anti-bonding, and the anti-bonding orbitals are indicated with a star. So if we look at the bond order for hydrogen, it will be 1/2 times, well, the number of electrons in a sigma orbital is 2, and then we're going to subtract off the number in an anti-bonding orbital, which is 0. So we have 1/2 times 2, or 1, which corresponds to having a single bond. But for helium, if we go to calculate its bond order, well, it has 2 electrons in a bonding orbital, but it also has 2 in a sigma star, an anti-bonding orbital, and so its bond order is 0, which means no bond forms. So this theory backs up something we already knew, which was that helium does not form a diatomic molecule and hydrogen does. Let's round up some of the vocabulary related to molecular orbitals. A bonding orbital is one that's lower in energy than the atomic orbitals. A non-bonding orbital is something like maybe where a lone pair is stuck, and it's probably going to be there at the same energy as the atomic orbitals. An anti-bonding orbital is going to be at a higher energy, and so when we stick electrons into there, we destabilize everything. HOMO stands for, I forgot to mention this on the previous slide, it's the highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital. And you'll hear a lot in more advanced chemistry classes about HOMO-LUMO transitions, which is where an electron jumps from that highest occupied molecular orbital to the lowest unoccupied. And in order for that to happen, you have to put energy into the system, like by zapping it with a photon. And just in case you couldn't read my handwriting 2 slides ago, bond order is 1/2 the number of bonding electrons minus the number of anti-bonding electrons. If you get a bond order of 1, that means a single bond, a bond order of 2 is a double bond, and a bond order of 3 is a triple bond. So in this video, we looked at some of the ideas behind molecular orbital theory, including delocalizing electrons and orbitals that are not confined just to one atom or to a couple of atoms, but can range over all of the atoms in a molecule. We generated the MO energy level diagram for the first row homonuclear diatomics, and we saw that it predicted that hydrogen H2 forms, but He2, helium-2, does not. And then we looked at some of those vocabulary words like bonding, anti-bonding, HOMO, LUMO, and bond order.